Okay, good evening. So this is our lecture number 22nd, and now we will change our approach of looking into the problems. So till now, our approach was from the point of view of a scientist or researcher. We were trying to see the individual fluid particles. Sorry, yesterday I have done. I think. Yes, already I have done. So now we will, so what we were doing earlier, so if you recall, then we have seen actually that uh, within a system, if we are having individual solid or fluid particles present, then how these individual solid or fluid particles are behaving actually, we were looking into these minute details. Okay. Now we'll change our approach for few lectures, and now we will look from the engineer's perspective. Okay, so in terms of engineering perspective, what we don't look into the minute details, but what we are interested in seeing the overall behavior of the system at the practical or industrial conditions. Okay, for example, if you consider that you have a flow pipeline, so in a flow pipeline, if you have a multi-phase flow, so it means that you have some continuous phase, and in that continuous phase you also having presence of some small fluid particles present in that. Okay, so you know that because if you have fluid particles present or coexisting with the surrounding continuous fluid, then the way your macroscopic parameters which were behaving earlier, these will not behave in the similar way as you would have expected their behavior in case of single phase flow. Okay, for example, if you have a pipeline, in a pipeline, if pure air is flowing, then you will be having your velocity profile and pressure characteristics of the system in some different manner, and you will be requiring some different amount of pumping power, okay, for achieving certain mass flow rate of the fluid. If in the same pipeline you add water, then of course your pressure characteristics and velocity characteristics will be changing, and you will be having some different value of the pumping power. On contrary, if you consider a system that you have a continuous fluid, and in that some other solid particles or fluid particles are present. Okay, so in that case, what will be happening now, your individual behavior of the macroscopic parameters, whether velocity, pressure, etc., will be actually different. Okay, but as an engineer, my interest is only to make my system work. Okay, I am not interested in minute details that what is happening within the pipe, but my overall goal is, say, I need to transfer some slurry from one location to a location, say 5 meters downstream or 5 kilometers downstream. So in a 5 kilometer long pipeline, my major interest is what should be my flow rate, and with that required flow rate, my particles should not suspend down and should not block the pipeline. So based on that, I will decide my velocity of the continuous fluid and size of the particles, so that these are remaining suspended as a fluid. And my second interest can be that I also need to decide what type of pump I should use for this pipeline, so that I can achieve this task done. Okay, so from engineer's perspective, my major interest is to determine the pressure drop. So say if P0 is pressure at this location, I need to measure pressure P1 at this moment. So I need to calculate difference of P1 minus P0, that will be my pressure drop, delta P. Okay. Then along with that, I have some minimum flow rate requirement. So mass flow rate of the fluid mediums which are flowing through that, and depending upon that, I need to simply decide my system for, say, I need to decide my pump, okay, which will be able to meet these requirements. Okay, and second interest of the engineers is, which majority of the times practicing engineers achieve through experience, is to reduce the operational cost. So for reducing the operational cost, their main requirement will be, they will try to choose configuration of the pipeline such that they are getting least pressure drop. So they will be investing lesser amount of money on providing power to the power to operating the pump. Okay. So majority of the time engineers, based on their practice only, they try to minimize these majority of the things based on their experience. But if they have to do major changes in the system, then of course they need to look from the fundamental perspective, and then they need to decide the things based on the fundamental behavior of the system. Okay, so in terms of looking the system from the bulk perspective, we will be using different modeling approaches. So one of the simplest modeling approach is homogeneous flow assumption. Okay, so the simplest of all the modeling approaches for multi-phase flows is homogeneous flow modeling. Okay, so let's try to see first this simplest approach. So as per homogeneous flow theory, we can say that this is the simplest technique for analyzing multi-phase flows. And what we do in this case, we consider our system. Say this is my system. In this system I am having a combination of fluids present. So what I will be doing, I will be trying to determine some average property of this mixture. Okay, and by using the average mixture properties, I will be treating my fluid medium using the single component system. And of course, whatever the averaged values of properties I will be getting, these properties are nothing but simply the pseudo fluid properties, whether, and these numbers are not indicated by any physical system. So what is the meaning of this? So if you consider, say, mixture of steam and say water, okay, so you will be having some liquid water in a container, and you will be having, say, vapor molecules, so steam of the same medium. So if you refer to this mixture, say I know that x fraction of vapor is present, x is the mass fraction of vapor present in the system. So I will be having certain density of liquid as rho L and certain density of vapor as rho V. So when I will be calculating the average property of the mixture, so average property of the mixture will be x times, or say my specific volume of the vapor is Vv and specific volume of the liquid is Vl. So if I calculate my average specific volume of the mixture, that will be nothing but x times specific volume of the vapor plus 1 minus x times specific volume of the liquid. Okay, so over here what I can say is that whatever the mean value of specific volume I will be getting, this number is something which is not acquired or shown by any particular fluid. Okay, because in fluid you have two different arrangements. If you go below this surface, then you will be getting value equal to mu L. If you go above this, you will be getting value equal to mu V. So it means whatever the average properties we calculate for the mixture, these are not shown by real fluid behavior. So these are not actual physical properties of the real fluids, but these are some numbers which are helping us in treating the system as a mixture, as a single fluid system. So that's why this type of averaging particularly refer to some property, and these, based on these properties, whatever the single component system we treat, we call that as a pseudo fluid. Is this point clear? Because these numbers are not shown by any particular fluid. Okay, so in a system, if you refer to different location, you will find only these two numbers, but bulk parameter of system I am calling as Vm. Okay. The third important point is, whenever we will be using the homogeneous flow theory, we have to consider equilibrium between the phases. Okay, so typically we know that there are thermodynamically different types of equilibriums: thermal equilibrium, mechanical equilibrium, and chemical equilibrium. Okay, so by meaning equilibrium, we assume that, by meaning the thermal equilibrium, we assume that there is no heat flow between the systems, okay, between different parts of the system. So it means that if I have a pipeline, and in that pipeline if I have small fluid particles present in continuous fluid, so my consideration will be that this temperature and outside temperature are actually same. Okay, similarly if I have a reacting system, so in case of reacting system there will be some chemical potential. So chemical potential of inside system and outside system should be same. And third thing is, of course, whenever I am moving from left to right, there will be change in the pressure. But if I refer to localized zone, in the localized zone, my pressure should be similar, and at the same point of time, another very important component is velocity. We know that in real system, velocity of the particle and velocity of the continuous fluid will be different, but whenever we consider this homogeneous equilibrium flow theory, we consider assumption that whatever the velocity of continuous fluid is there, same is the velocity of the particle. So it means there is no velocity difference between particle and the continuous fluid. Is this point clear? So major assumption of the homogeneous flow theory is that my fluid particles, or in more generic sense, all the phases are nothing but in equilibrium. Okay, so if all the phases are not in equilibrium, in that case I cannot apply homogeneous flow theory with reasonable accuracy. Now again you will be finding that in the practical scenarios, rarely you will find a system where everything will be in the equilibrium. So in practical scenarios, of course, there will be many non-equilibriums will be existing, but the major assumption is whatever theoretical analysis we do, even for the single phase flow system also, there is the, between the idealized theoretical analysis and the practical conditions, there is some error percentage of 10 to 20%. Okay, so if we are going with that much large error range, so even for many multi-phase flow simulation, multi-phase flow situations, we can obtain the analysis of the system by using this assumption with the accuracy of 20 or 25%. So that is a reasonable accuracy for starting with the practical systems. Okay, so that's why we can still continue this theory. Even from the fundamental perspective, this seems that in practical scenarios we may not have perfect equilibrium between the phases. Okay. So for certain situations, this will give good accuracy, like within the range of 20%. For certain situations where the assumption of theory is violating or deviating a lot, there you may feel that your results in real scenarios are changing, say by 50% or 60% from the actual values. Okay. Then, so with this we can see that what are the situations where this theory cannot be applied. So if you have rapid acceleration and pressure changes, which makes equilibrium theory inaccurate. So in certain system, if you have the significant acceleration of the fluid mediums, so there you will be finding that existing equilibrium, particularly the velocity equilibrium, means same velocity of all the phases in the accelerating zone, may not be practically feasible. So there we will be having lot of inaccuracies, and flashing of steam water mixture through short nozzles or orifices, one typical example where acceleration of the fluids is rapid and homogeneous flow theory does not work there. Okay, so now can you tell me what do you mean by flashing? What do you mean by flashing? What is the phenomenon of flashing related to phase change heat transfer? Any one of you have heard the name flashing before? Flash chambers, when we study this course on refrigeration, there we use the flash chambers. Sorry? So we use flash chamber to separate liquid and vapor. But what is the phenomenon of flashing? We use throttle. In throttle also we say we are not adding any heat, but still some liquid is converting into vapor. So why that liquid is converting into vapor? That is converting into vapor because of the phenomenon of flashing. All of you use capillary tube or throttle type expansion device in your refrigerator, fridge, vapor compression refrigeration cycle. Okay, so what do you see on the pH diagram or any diagram of the system? So if you plot pH diagram, then what do you see? This is your condenser. At the exit of the condenser, I have subcooled liquid. Okay, sorry, saturated liquid. And when this saturated liquid is passed through a throttling device, through a capillary tube, then what happens? It enters into lower pressure, which is nothing but evaporator pressure. Here this is PC, which is greater than PE. And then this process in the throttle is represented by a dashed line. And then at the entry of the throttle, we are in pure liquid region, and then in the exit of the throttle we are in the mixture regime. So it means here I am having presence of liquid plus vapor, but within the throttle we are not adding any heat. So despite being the fact that we are not adding any heat, still some portion of the liquid is getting converted into vapor. So this is nothing but phenomenon of flashing. Okay, so rapid change of liquid to vapor because of decrease in pressure below the saturation pressure is something which is called as flashing. And change of liquid to vapor because of temperature greater than saturation temperature is something which is called as boiling. Okay, so you should know these fundamental things. If you don't know, then I have given you an example, but you will not understand what I am talking about over here. Is this point clear? Yes, this is a throttling device. Within the throttling process, liquid is getting converted into vapor because of decrease in pressure. So that is something which is called as flashing. Okay. Throttling is a process of decreasing the pressure. Okay. So in a throttle, you can decrease the pressure of a gas also, pure gas also. You can decrease the pressure of a liquid also. But if during the throttling process, liquid is converting into vapor, then only you will be calling it as a flashing. So if you do throttling of a gaseous medium whose inlet state and outlet state inside a throttle both are in gaseous phase, then you will not be calling it as flashing. So flashing is conversion from liquid to vapor because of the decrease of pressure. Is this one clear? So you should have clarity of these concepts. Okay. So means flashing of steam water mixture through short nozzles or orifices. So if you see in flash chamber also what we do, before the flash chamber we put a throttle. Okay, we put a nozzle. When the fluid comes through that nozzle, its pressure decreases at the outlet, and because of the low pressure, some part of the liquid gets converted into vapor. That vapor we collect at the top of the tank. We take it for some other purpose and liquid we replenish. Okay. So, in this type of phenomenon, because whenever this flashing happens, this is a rapid phenomenon. Okay. So, there you will be finding that there will be rapid acceleration of the fluid medium, and in between liquid and vapor medium, velocities will be significantly different. If velocities are significantly different, then this homogeneous equilibrium flow assumption will not be applicable. So, that's why if you use this theory, then this will be giving you inaccurate results. Okay. Then another is counter current gas liquid flow in a vertical tube under gravity. So if you consider a vertical tube, and in that vertical tube if you see that liquid is falling down and gas is rising up from the center core. So now one is moving in downward direction, other is moving in the opposite direction. So in this scenario, how you can make the reasonable assumption of same velocity for both phases? You cannot do. So that's why you cannot apply homogeneous flow theory under these circumstances. Is this point clear? So whenever you are choosing certain theory, you should also know the situations where you can apply this theory or where you cannot apply. Okay. Is this point clear? Yes, we can use inside a boiling tube. This is used. We will see. Yes. Heat exchange is happening from outside, but within the system during the phase change process, all the liquid is getting converted into vapor at the saturation temperature only. So temperature of vapor and temperature of liquid during the phase change processes are remaining same. So that's why this can be applied for boiler and condenser tubes. Okay, maybe if we are able to do this theory, if we are able to complete this theory today, then in next lecture I will show you one numerical problem of boiler tube where we can use this theory for prediction of the pressure drop. Okay. So now let's talk about the homogeneous flow theory. So as based on the underlying assumptions what we have taken earlier, based on these assumptions, the first point is we will be applying now this theory for one dimensional steady homogeneous equilibrium flow. So when I am referring to one dimensional thing, it means I am interested in estimation of area averaged properties. Is this point clear? We have already talked about this. One dimension meaning is we are not seeing variation with area. We are only seeing the variation along the length of the pipe at different points along the length of the pipe. Okay. So that's why whenever I will be writing the governing equations over here, I will be writing one dimensional governing equations. Okay. And at the same point of time, because the major idea of homogeneous flow theory is that we have to go with the mixture properties. So if we have to go with the mixture properties, I have to write over here combined phase equations. Is this point clear? Combined phase means if I write individual phase equations and take their sum, then whatever the equation I get, that is nothing but for all the phases present in the system. So because I am using the homogeneous theory which is based on the mixture approach, so I have to write over here combined flow equations. Okay. So if you see, this is my first equation. So if I consider that whatever the fluid is flowing inside this, that is having some mixture density of rho m. Okay. So I can write my mass flow rate, which is given by symbol W equal to rho m into velocity. Now velocity of both the phases will be same. Okay. Multiplied by area. So rho m velocity into A equal to constant. This is my assumption. Of course, I have drawn over here a pipe of constant cross section. So my more generic system will be where pipe can also have variable cross section and the pipe can be oriented at certain angle theta from the. Okay. So pipe may not be parallel to the ground. Okay. And of course, even in this inclined system, whenever I am using the 1D flow assumption, I am writing my equations along this line. So this is my x direction. Is this point clear? So this is my continuity equation. Then I have to come for the momentum equation. So sorry, let me not write it x, let me write it z direction. So if along the length my direction is z, then I will be having, and of course steady flow assumption I have taken, so I will not be using any time term in my equations. Okay. Now I have to consider the convective component. So convective component means if my area is changing, then of course in the z direction I will be having variation of velocity. So dv by dz is variation of velocity along the z direction and w is mass flow rate. So this is nothing but rate of change of momentum. This will be equal to all the forces which are acting. So first is pressure force. Pressure force will be dp by dz into area. Okay. Then I will be having minus, what is this P? Tau W into P. What is tau W? Wall shear stress into P will be perimeter. Okay. And then I will be having this rho mg cos theta. Now because I have to consider the component of the gravity along this direction. So component of the gravity will be coming as cos theta, and then A area, because I am doing area averaged equation, so that's why I have multiplied area over here. Okay. Then what I need to do next? So this is what? This is my momentum equation. Okay. Next I need to write down the energy equation. So what about energy equation? dQE by dz. So this is any heat transfer from outside heat interaction with outside. So QE is my heat interaction from outside. Okay, so heat interaction from outside per unit length of the pipe I have written over here. Similarly, this is work interaction per unit length, that is equal to mass flow rate of the pipe into d by dz of property. So this is my, yes, where dv by dz is actually your acceleration, rate of change of velocity with the length. So, and w is mass flow rate. So this is rate of change of momentum along the length of the pipe. Yes. Is this one clear? So this is my energy equation. All are clear with these equations? Now, this particular second equation, pressure equation, because as an engineer, my interest is majorly in determining the pressure drop. Okay, so my interest is in determining the pressure drop. So, pressure drop, if I take to the left hand side, so I can write dp by dz is nothing but equal to, I will divide with minus a throughout the equation. So, I will get minus p by a into tau w minus w by a into dv by dz minus rho n g cos theta. Okay, so ultimately this is nothing but wall shear stress. So this is contributed because of the viscosity of the fluid, and ultimately we call this as nothing but our frictional pressure drop. So this is my frictional pressure drop. Then W by A into dV by dz. What dV by dz is representing? dV by dz is representing acceleration of the fluid. Okay. So this is my accelerational pressure drop. So pressure change because of acceleration. And what is this? This is the contribution of the body force. Okay, so pressure change because of change in elevation. Okay, so once you will be having change in elevation, then you will be having this pressure drop. So what I can do, typically what is done, because our major interest as an engineer is to look into the perspective of pressure drop, so that's why all these individual terms we call first term on the left hand side as frictional pressure drop, second term we call as acceleration pressure drop, and third term we call as gravitational pressure drop. Okay, why this separation is necessary? Because if your interest is to improve the system, then you know that certain things are there which you cannot change. For example, if you have certain amount of elevation which you have to achieve, then you cannot change your gravitational pressure head. You have to think of changing your acceleration and the frictional pressure drop. So that's why many times it is required to look into the individual details of the pressure which is actually occurring as a total component. Okay. Then dp by dz, so total dp by dz I can write as the sum of all these three individual components. Okay. Now we will look into the details that how these individual pressure drops we can present in terms of two-phase flow parameters. Okay, multi-phase or two-phase flow parameters. Yes. What I told you, we are using the 1D flow approximation. So as we are using the 1D flow approximation, it means we are substituting only the velocity which is coming as area average velocity. Okay. Okay, so certain relations we need to see so that we can further deduce these pressure terms in terms of the two-phase or multi-phase flow parameters. So first relation is mean density. We know that we can write it alpha into rho 2 plus 1 minus alpha into rho 1, where alpha is nothing but volume fraction of phase 2. So alpha is volume fraction of phase 2. Okay, that's why I have written alpha into rho 2 there. Okay, and at the same point of time we also know that as we do in case of thermodynamics, we say that mixture specific volume Vm is equal to x times V G plus 1 minus x times Vf. Okay, so that is something which we write in thermodynamics. So this V is nothing but 1 by density. So 1 by rho m into x by rho 2, 1 minus x by rho 1, considering that x is mass fraction of phase 2. Is this point clear? Now, these are two simple relations which you can easily derive. X into rho m can be written in terms of alpha into rho 2, and 1 minus x into rho m can be written in terms of 1 minus alpha into rho 2. Can you derive this? Can you derive these relations? What is x? X is nothing but mass fraction. So it will be m2 divided by m1 plus m2. m2 can be written in terms of density of phase 2 into volume of phase 2, V2, sorry, not specific volume, V2, okay, divided by this mixture mass can be written in terms of mixture density into total volume V1 plus V2, okay. Now V2 by V1 plus V2 will become alpha. So it means alpha, so then you can take this rho m to left hand side, so x into rho m will become alpha times, okay. These are again the simple relations we have seen earlier, that alpha can be written in terms of Q2 by Q1 plus Q2 for area averaged quantities, which is J2 by J, and x can be written as mass flow rate W2 by W1 into W2, which can be written as G2 by G. Okay. Now comes the another perspective. Whenever we calculate wall shear stress, okay, so estimation of wall shear stress is actually challenging, and whenever we are considering the homogeneous flow approach, in case of homogeneous flow approach, we are not looking into variation of velocity along the radial direction. So that's why we will not be able to predict the actual value of velocity profile at the wall. So if we are not able to predict the derivative of velocity profile at the wall, then from theory we will not be able to find the value of wall shear stress. So it means we have to look from certain other forms to determine the value of wall shear stress whenever I am applying the homogeneous flow theory, particularly based on one-dimensional approximation. Is this point clear? So what I will be doing for that, we know that in general sense wall shear stress can be written in terms of Cf into half rho v square. So here I am using the mixture property rho m into v square. Is this point clear? And then if I use this formulation, then in my previous equation of frictional pressure drop, I can replace wall shear stress with this value. Is this point clear? So previously I have defined a separate component for frictional pressure drop, which was minus P by A into tau W. So there tau W I am replacing with this relation. So once I replace with this relation tau W, I will be getting 2 Cf rho m into V square by. Okay. Now I will take the help of these two relations, and by taking the help of these two relations, what I will do, out of this rho m into V square, I will write it as rho m into V into V. So 1 rho m into V I can replace with G, and this V I can replace with G, where G is nothing but total mass flux of the mixture and J is total volumetric flux of the mixture or total superficial velocity. Okay, so total means J1 plus J2, G means G1 plus G. Is this point clear? So for a total system, the mixture velocity will be equal to superficial velocity. Is this point clear? So that's a very simple question. So for a total mixture velocity, local mixture velocity U will be equal to nothing but the superficial velocity of the mixture. Okay, is this point clear? So by doing these substitutions, I can write my dP by dZf as 2 times Cf into Gj by D. So in place of rho m V square, one I have replaced with G, other I have replaced with J. So G into J by D. Is this point clear?
सर पाया एक पाया आना चाहिए हमने एरिया को पाई आर स्क्वायर पाई डी स्क्वायर बाय 4
No, we have not written.
नहीं माइनस डी पी बाई डी जेड
हाँ हाँ.
जब हम इस जो आपने पहले फॉर्मूला लिखवाया है उससे इस फॉर्मूला पे आएंगे तो सर
this is perimeter. Okay, so pi will cancel out very quick. Okay, so now v, which can be written in terms of g by rho m. Okay, so that can also be written in terms of this value, g times v1 plus x times v1. So this is some another formulation for v, and using this formulation, this v you can also replace and make it one g is coming from here, other g is coming from rho m into v, and this will become g square by d into v1 plus x times v1. So what is the benefit of this equation? Can you tell me what is the benefit of this equation in comparison to this equation? The benefit from this point to this point is that now if you consider a pipe in which mass fraction is changing along the length of the pipe, then depending upon the local value of mass fraction, actually you can calculate the frictional pressure drop. Is this point clear? It can happen that in a system, whenever at the entry point, if you consider a boiler tube, so in a boiler tube at the entry point, mass fraction is 0. When you go further, then mass fraction value slowly starts increasing. Further downstream, if you go, it will be becoming very large value. Okay, so it means that for a very generic system, your mass fraction can change along the length of the pipe. So it is better to represent our value of pressure in terms of mass fraction, local mass fraction, so that whenever I am applying it for generic system, I can take into account the effect of the change of mass fraction along the length of the pipe. Is this one clear? All are clear with this idea? Okay. So this relation I have now presented in more generic way by taking into account the mass fraction. Okay. Now let's talk about second term. That is my acceleration pressure drop. So in case of acceleration pressure drop, this is my formula, g times dv by dz. Okay, and of course this v can be written in terms of w by a into rho m. And what will be w by a? W by a will be another g. So this further can be written in terms of g square into d by dz of 1 by rho m. And then, so basically what I have done over here, this w by a I have first written as g, and then I have applied the chain rule to calculate this d by dz of g by rho m. So this will be giving me two terms in expansion, something like this. Is this point clear? So after this expansion, what I will be getting that d by dz of 1 by rho m can be written in terms of dx by dz into 1 by rho 2 minus rho 1 plus x times d by dz of rho 2 plus 1 minus x times d by dz of 1 by rho 1. So this is nothing but expansion of this d by dz of 1 by rho m, considering rho m equal to considering rho m equal to 1 upon Vm and Vm equal to 1 minus x into V1 plus x into V2. So if you do these substitutions and then expand, then you will be getting this particular equation. Okay, so let's not go into the mathematical details. You will try, you will get this. Okay, but we will try to understand the major physical reason. So now what I can do, this 1 by rho 2 by minus 1 by rho 1, I can write it as V2 minus V1. And V2 minus V1 typically from thermodynamics nomenclature or even from multi-phase flow notations also, we can write it as V1, 2. Okay, you have to understand it very clearly. There is difference between this V and this V. Can you tell me what is the difference? This is velocity, this is specific volume. So understand the difference. Okay, Don't consider that both the symbols are actually the same. So this further can also be written in terms of, okay, now from this step to this step there is one interesting fact. So in what scenarios do you expect that your mass fraction will change under the steady state conditions? If you have an adiabatic flow, in an adiabatic flow, if you are operating under steady state conditions, then within a pipe, if you are entering fluid 1 and then you are also entering fluid 2, if you call the conditions to be steady state, you have to keep flow rate of fluid 1 and fluid 2 same at each and every time. Okay, so in adiabatic situation, whatever the distribution of these flow rates will be giving certain flow pattern, that flow pattern will remain almost same under the within the pipeline. Okay, but there will be only change of flow pattern if within the pipeline fraction of the fluid is actually changing. Okay, so fraction of or amount of fluid is changing within the pipeline itself. For example, in case of boiler tube or condenser tube. So where in case of boiler tube, your more vapor is generating, so quality is increasing as you are moving along the length of the pipe. And in case of a condenser tube, as you are moving along the length of the pipe, your quality is decreasing. Okay, so only in the scenarios of phase change heat transfer, you will be experiencing that your quality is actually changing with length. Okay, it is changing along the length. So that's why what we need to do now, we have this change of specific volume dV2 by dz and dV1 by dz. So these changes in specific volumes are particularly in case of two-phase flow conditions, we are involving phase change heat transfer like liquid and gas medium. These changes takes place under the saturated conditions. Okay, and saturation conditions are nothing but controlled by corresponding value of the pressure. Is this one clear or not? So what I am saying is, this is one interesting fact, let me explain it again. So if you have a say PV diagram of a substance, so in case of PV diagram of a substance, what will be happening? This is my one pressure line, this is another pressure line, this is third pressure line. So here say this is P1, this is P2 which is greater than P1, this is P3 which is greater than P2. Okay. So whenever you have a two-phase flow pipeline, you will be finding that, of course, any pipeline you have, at the upstream direction you will be having high pressure, and in the downstream direction you will be having low pressure. Okay. So when you are moving along the z direction, you are moving from high pressure to low pressure side. So when you are moving from high pressure to low pressure side, so in the high pressure zone, your liquid and vapor will be located at these 2 points. This will be liquid value, this will be vapor value. So here V1 and V2 will be these 2 values. When you will be moving to P2 pressure, so say you are getting some point where pressure is P2, there your liquid and vapor phase are now corresponding to the new thermodynamic state, and that state is represented by these 2 points. Whenever you enter further and you enter into the pressure condition of P1, then you are reaching to the these 2 new thermodynamic states. So it means that in a two-phase flow pipeline where your phase change heat transfer is there, okay, you have the combination of a liquid and gas phase of a pure substance. When you are moving from one end to other end of the pipeline, as your pressure is decreasing, your thermodynamic state of the individual substances is also changing. Is this one clear or not? So that's why whatever the value of V1 and V2 we are considering, that V1 and V2 are changing along the length. Basically, these are the thermodynamic properties which are changing because of changes in thermodynamic property. So it means we are, and particularly whenever I am considering the liquid gas combination, I am operating within this liquid vapor dome. So once I am operating in liquid vapor dome, within the liquid vapor dome, variation of property is dependent upon any single independent intensive property. Okay, so that property I have assumed that when I am moving along the length of the pipe, say my pressure is changing. So I will be writing that my volume is nothing but function of pressure, and pressure is something which is function of Z. So that's why this term dV2 by dZ I can replace as dV by dP into dP by dZ. All are clear with this idea? Okay. So volume is specific volume of the individual phases is function of pressure, and pressure itself is something which is varying with distance. Okay. So that's why this dV2 by dZ I am replacing with dV2 by dP, and dP is changing with dZ. So ultimately my dP is cancelling, I am getting dV2 by dZ only. All are clear with this idea? Okay. So that is the transformation from this point to this point. And remember, whenever we are deriving these equations, this is the most simplistic theory of solving multi-phase flow problems. Okay. So now what I have done, I have replaced my dP by dZ term with this entire quantity. All are clear with this? And in this you can see that this first component is contributed because of the changes in thermodynamic properties, and second component is contributed because of the changes in area. So it means acceleration component can be further split into two parts. One is because of the acceleration because of the change in area, and second is acceleration because of the change of mass friction within the pipe, and this change of mass friction is actually associated with the other heat transfer or pressure. All are clear with this idea? Yes, please. Sorry? Vertical line, yes. Yes. Huh? Sorry? Why? Because this vertical line, na? Huh. So pressure is changing. Why? What I am saying is this specific volume is function of P. Where I have told you volume fraction. This is dV2 by dZ. I told you that specific volume is function of P, and P is function of Z. Okay. Where I told you volume fraction is function of P. I told you volume of individual phases is function of P. Okay. Is this point clear? See, if you are at this point P3, high pressure point, corresponding to that also at any pipe cross section you will be having mixture of liquid and vapor. So when you have to determine the individual property of liquid and vapor, what you will be doing? You will be referring to this diagram, and in this diagram corresponding to P3 you will see where is your saturated liquid, where is your saturated vapor, and then you will decide your V1 and, sorry, I am doing one mistake, I am writing V1 and V2 wrongly. So this should be saturated vapor V2 and this is liquid V1. Okay. And if you go to now new pipe cross section, in the new pipe cross section again you have mixture of liquid plus vapor, and corresponding to this liquid and vapor mixture, now you have thermodynamic states as V1 and V2. Then if you go to third state, then your mixture states are V2 and V1. So it means when your pressure is changing, the corresponding specific volume values are changing. So that is what I have written, specific volume is function of pressure. Okay.
सर डायरेक्टली हम V2 को लेंथ की उसके रिस्पेक्ट में निकाल नहीं सकते, इसलिए हमने अलग अलग किया हुआ.
Yes, that's why, because V2 is a strong function of pressure and pressure is a function of length. That's it. So I cannot find out the exact value of V2 with Z, how it is varying. Okay, because V2 is a property. It will be depending upon the properties, not only the physical parameters. Okay, means physical parameters means which are related to the problem like length of the pipe. Okay, understood?
सर जैसे 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 आगे बढ़ रहे हैं वैसे वैसे प्रेशर हमारा घट रहा है तो अगर हम बॉइलिंग फिनोमेनन तो उसमें बॉइलिंग बढ़ेगी जैसे जैसे आगे बढ़ेगी
Yes. We will be having, because saturation temperature will go down, so there will be enhancement. Okay, is this point clear? So it means that acceleration component can be because of now two things. One is because of area change and other is because of the change in x or change in properties which are majorly occurring, which are majorly changing the value of x also. Okay. Then comes third component. It is very easy. So dp by dz into g. So this was rho g cos theta, and rho you have written as v1 plus x times v1. So now what I need to do? I need to do summation of all these quantities to get my total pressure drop. So this is my total pressure drop equation. Okay, so this is nothing but my total pressure drop equation. If you have to calculate pressure, then you need to solve this equation. And this total pressure drop equation can be written to this generic form. Okay, so this is the sum of all the previous equations which is giving me this final equation, and this final equation can be written in simplified way with the help of this particular formulation. And in this formulation you can see this first factor CF, CZ, CA and CG, all these are something which are called as influence coefficients. So these are nothing but called as the influence coefficient. So when you are referring to CF, then you need to compare with this equation. So this entire quantity is becoming your CF. So it means this is influence coefficient because of friction. When you compare this Cz into dx by dz, so this is dx by dz, so this value will become your Cz. Now what is dx by dz? Dx by dz is change in quality along the length of the pipe. So it means this Cz is influenced coefficient because of phase change. Because when phase change will be happening, then only your quality value will be changing along the length of the pipe. Okay, so this is influence coefficient because of phase change. Then if you compare the third one, 1 by a into dA by dz into Ca, so this will be becoming your influence coefficient because of acceleration of the fluid, and this acceleration is associated because of the change in area of the pipe. Okay, and then final is very simple, this is because of the gravitational field, and then you have some term in the denominator, and this term in more generic sense can be equated to 1 minus m square, where m is nothing but over here Mach number. Okay, so if you equate this denominator to 1 minus Mach number square, you can determine what will be the speed of sound in your homogeneous mixture. Is this point clear? See, till now we are doing very generic thing. It means whatever the analysis we are doing, this is applicable for, if you account for variation of density, then it is applicable for compressible flow also. Okay, so you have involvement of Mach number also over here. Okay, is this one clear? All are clear up to this point? Now let's talk about some system in which variation of quality is not only, variation of property is not only influenced by enthalpy, but it is also dependent upon some other parameter. Okay, so if you are not operating within the saturated regime, but you are operating, say, somehow some away from the saturated regime also. So in that case, what will be happening? We have to account for variation of quality as function of two parameters, and there, if you do this, then ultimately this will be your pressure formulation. Okay, is this point clear? So let me stop at this point only, and then we will have further discussion in the next lecture, and probably we will also get some time to solve one numerical problem based on the homogeneous flow. Okay.